All right, let's take a look at how changing temperature affects equilibrium and is related to Le Chatelier's principle. So a change in temperature actually changes the value of the equilibrium constant, meaning it's going to change the numerical number. It's going to either make the reaction more favorable or less favorable, depending on whether the reaction is endothermic or exothermic. Now, we can predict the effect of the temperature change by considering that an endothermic or exothermic reaction can have heat written in as a reactant or as a product, or thinking about writing them in if it's not already there. This first reaction with hydrogen and iodine to make hydrogen iodide, or hydriodic acid, um, is exothermic. And that can be shown in one of two ways. Heat is a product, or delta H being negative tells me it's exothermic. The second reaction, I have N2O4 turning into two NO2s. Again, it's an endothermic process, and I know this either because heat can be written in as a reactant, or I have a positive delta H. A lot of times you might be given these delta H's without the heat being written in the reaction, and I always just like to write them in to have that as a visual to think about. The simple way of thinking about this is treating those as reactants and products and kind of thinking it back to concentration. If I increase the temperature, then that means more heat. And whatever side has the heat on it, the opposite side also has to go up. So it's going to favor the side without the heat. Decreasing the temperature is the same. It means less heat, which means that I'm going to favor the side that has the heat. Now, typically what this means when I'm saying favoring, if reactants are favored, that means the reaction doesn't want to go forward very much, and so K is going to get smaller. If the products are favored, then that means that the reaction is proceeding, and that means K is going to increase. So these questions typically look something like this. Predict how the change in temperature will change the equilibrium constant K for the following three equations. Now I just have increasing temperature for the first two, and the third one is decreasing the temperature. Again, we're going to want to focus on what does the delta H tell me about the reaction. So pause the video, write down your answer into what you think will happen to the value of K, and then unpause and see how you did. So here we go. Starting with the first one, since I have a positive delta H, it tells me it's an endothermic process. I can write that heat in as a reactant. If I increase T, that means more heat is going in. Heat is a reactant, so that means more products have to be made. More products means the reaction is more favorable, and that means K is going to increase. On B, I have a negative delta H. This is an exothermic process, so I can write the heat in as a product. It's coming out of this reaction. If I increase the temperature, I'm adding more heat. Now I have more heat, but the heat's a product, so the reverse reaction is going to start to become more favorable. Or, in other words, the reaction itself, written in the forward direction, is less favorable, and K is going to decrease. Now, if I decrease the temperature in the third one, I'm going to look at delta H. It's a positive delta H. It's an endothermic process. Decreasing the heat means less heat. I'm creating a hole, less reactants. So I'm going to need to fill that hole. It's going to favor the reactant side. Again, we're going to see a decrease in K as I'm going to need to make more N2O4 to offset the fact that the heat is going away. Now there's one last part, and that deals with adding a catalyst. And a catalyst does nothing, absolutely nothing. It speeds up the forward reaction and the reverse reaction the same, so the position of equilibrium doesn't change.